to work?
Yep, we're good. All right. Hello, everybody. Okay. Questions, I guess, or however you want to run this.
Yeah, I think the way we had talked about this was students ask questions, and we're happy to elaborate, answer those questions. Any questions fly. The moment all the questions stop, we stop. So like I said, this was going to be very unscripted. We don't have any slides, but yes.
Yeah.
Am I allowed to ask you guys to go over all questions?
Yes, if
No one else has anything.
if nobody else has anything, then yes. But if it's really going to take us a long time, what we might do is answer the concept there and explain, how we came to that answer instead of going into all the details.
I do have a question about quiz 2, the last question. Didn't catch the PTE. That one you're not too sure how to approach it.
You'll have to speak a little bit louder.
Quiz 3?
Last question, Q13.
So like.
How do you?
Oh,
Sorry, is this still on?
Yeah, but it's really, it's pretty good. Like this question from quiz 3? Okay. Where do you want to start with it? Here, we can start with quiz 3. So this, yeah? Okay, so we created an experimental machine, 12-bit virtual addresses, 8-bit physical addresses, page size 16 bytes, page table entry size of 1 byte. Our page table entry is the following layout, so it is 1 byte, and that's the layout. So, is there like a specific part of that you have a question about, or just the whole thing? Okay, so if we're translating any address, well, we need to know how many levels of page tables we have, right? So we have a 12-bit virtual address. We have a 12-bit virtual address. We want, we have a page size of 16 bytes. So our offset, we need 4 bits to address all 16 bytes, right? And then if we have a multi-level page table where each page table fits in exactly a page, we need 4 bits for each index in that smaller page table. So each level would be 4 bits, and we have 2 levels, right? Because we'd have, so like at the bottom, I will add more. So if we have a 12-bit address, we know that 4 bits are the offset, and then we'd have 2 levels of page table that are each 4 bits like that, right?
Do you understand why we need, in the 8 bits that are required to store the page number, do you understand why we're breaking that into 2 4 bits?
So the trick for all these, for knowing how many bits you need for each index level, well, we're trying to fit everything onto a page. So everything on a page, it's like page size equals, so if this was in C, and I said it was a char, which is, we know that's only 1 byte, right? Then the question is, how many chars can I store on a page if I know the page size is 16 bytes? Yeah, right, and if the PTE was bigger, if it was like 2 bytes, how many could I store on a page? No, so if my page table entry is 2 bytes, how many could I store on a 16-byte page? 8. Right? Or if
So
it was
here in this question, we had said that a page table entry is 1 byte, right? And the page size is itself 16 bytes. So that means we can store 16 page table entries in a page, which contributes to the 4 bits and the low and the high. Because we have 8 bits, we need to be able to address 8 bits, right? But both the top level and the bottom level page tables can only store 4 bits worth of page table entries. Does that make sense?
Yeah, okay, so if I had that, that's like for every question, it's like the number of index bits you need if everything fits on a page. So however many I can hold, that's how many different pages I can point to. So for this, I can only fit 16, it's 1 byte, so each page table stores 16 bytes, it could be 16 entries. So in order to address 16 things, I need 4 bits. So 0, up to 15. So that'd be 16 things.
As an example, let's say the page table entry was 2 bytes. Okay? In this example, how many levels of page tables would we have needed? We have 8 bits for the page number. All right? And let's say the page table entry was 2 bytes. Page size is still 16. How many levels of page tables would we have needed?
2.
Why 2?
Double.
Okay, my theory is that, so you have a 16-bit virtual address, you know that 4 of the bits are reserved for the offset, so you're like, okay, so now I have 12 bits remaining, or,
No, we have 12-bit virtual addresses.
oh, sorry, 12
Yeah.
bits. Okay, so we have 8 bits remaining for the virtual address, like for the page tables and stuff. So you're like, okay, page size, how big is the page?
Page size is 16 bytes.
So you're like, okay, I have 16 bytes per page divided by 8?
Let's say that the page table entry we had told you was 2 bytes.
Okay, then 2 bytes. So then you're like 16 divided by 2 is 8. So you can fit 8 page table entries within like 1 page table.
Okay?
So then you're like, okay, so I have 8 bits remaining for virtual address. So I just like divide that into
So how many page tables would I need?
4? No.
3.
You're almost there.
The math in my head.
It's 3, so 8 page table entries per page. So that means you
Which
have
can address 3 bits.
3 bits.
But we have 8 bits in this example, right? So how many levels would we need? 3, 3, 2. Make sense? Here we had 16 page table entries that can, in that case, we can address 4 bits of that page number. That's why we have 2 levels. So depending on the page table, depending on the page size, depending on the page table entry, that tells you how many page table, size of the page table entry tells you how many page table entries will fit in a page. Based on that, that tells you how many bits of that page number can be used to index into that page table. So with 8 bits there, if only 3 bits can be used per page table level, then we need at least 3 levels. So we made that simple by only giving you, 4 and 4.
Yeah. So in that case, like this was all the variants, so you got one of these. So the questions said, well, there always has to be a highest level page table. That's the starting L1 that you'll be given. If this was like, had multiple processes and stuff, when you context switch processes, you would change whatever page table that's pointing to, which would effectively change the address space with just a single pointer. So some people got tripped up by assuming that it starts at 0. It does not start at 0. So it says highest level page table starts at ppn 2. That's physical page number 2. So it is the second index 2 physical page. So this is the 0th page on the machine, these 16 bytes, because page size is 16 bytes. Everything would be aligned to 16 bytes. So this would be 0, this would be 1, and this would be 2. So these 16 bytes are all of our page table entries.
Another way, just mathematically, we asked you for physical page number 2, right? And what's the page size? 16 bytes. So you shift this by 16 bits, right? Which is in hex. Because one of these zeros is 16. Sorry, 4 bits. Sorry. All right, so that's why the physical page number starts at 20.
Yeah, or another way you can think of it too is that, hey, for both, if we have like a very general case of like a virtual address and a physical address, well, the top bits of the virtual address are the virtual page number, and the bottom ones are the offset. And for physical, it's just the physical page number or physical frame number, whatever you want to call it, and then the offset bits. So if I say, hey, it's page number 2, that just means this part is 2, and no matter what the offset is, even if I say, hey, page size, say it's 4 kilobytes, like that, which is, so it's always helpful to just write powers of 2, which is 2 to the 12, so I have 12 offset bits in there. If I say it's, my page size is 4 kilobytes, and it's physical page 2, well, the addresses that corresponds to are 2000, all the offset bits are off, 2, F, F, F. And you can double check yourself because that's 0 all the way to 4095. So, which is the page size, which makes sense. Everything's byte addressable, so nothing's going to change. So, in this example, this is our highest level page table. So if you had any of the variants that started with a 1, you just go to index 1 in there, and everything is 1 byte. So I just move 1 byte at a time. So this would be index 1 into this table. So 0, 1. So it's this entry. And
okay, just
yeah.
so again to clarify, so you've got that first page starting at 20. That's the high level, the top level page table, right? Now in this case, each of those entries, each byte is a separate page table entry. That's why we have 16 page table entries there, right? And that is why the top 4 bits of your address in the page number can be used to index there. Okay, so this is why, for instance, this 1 is saying it's not 0, the second entry, because that's the 0th entry, this is the first entry. Okay, now just to be clear, if you had page table entries that were 2 bytes, not 1 byte, then where would this entry 1 be? It would have been the second and third entries, 0, 1. It would have been, those 2 entries would have been the page table entry if the page table entry was 2 bytes. All right, so we're taking into account that each page table entry is 1 byte, and then using this value to index into the page table.
Yeah, and I mean, it's the same thing if it was like 4 bytes. Well, this is the 0th entry, these 4 bytes, and then the next 4, and then the next 4, and the next 4. And you can always double check yourself because you have to index everything in there. So, like, if I told you instead of a PTE being 4 bytes, and I just said it was an int, and this is an array, you could tell me how many things fit within a certain number of bytes, right? So it's the same thing, so you don't need to get tripped up on that. So for this, anyone that starts with a 1, index 1, so it's 0F, or sorry, 1F. So if you look at the layout of the PTE, the bottom 4 bits, so nicely, the 1 hex character is 4 bits. So the bottom one is all 1, so it means it's valid. For most of these, we only care if it's valid. And then the physical page number is 1. So, and because this is a multi-level page table, that is the physical address where the L0 page table starts. And it's going to be the same principle that we used to get the L1. So the L0 page table would start at address 10 and go all the way to 1F. So it would also be 16 bytes, which corresponds to this one. Sorry, I wrote over it before. So it corresponds to this one. So now for address 1, 2, 3, so our L0 index is 2. So this would be index 0 because everything is 1 byte, index 1, index 2. So this would be the entry FF. So because it's FF, we look again. It's valid because the last hex character is an F, so that's definitely a 1. And then the beginning F is the physical page number, and this is the lowest level page table. So we essentially hop through everything, and to get the physical address, we just take that physical page number and then keep the offset the same. So this address would be, we found it, it's F, so it would be F3 because the offset is kept the same. So the last 4 bits we used for the offset, so we wouldn't touch that because it's still referencing some byte in the page. So we don't touch that. So you never have to translate the offset. Yeah.
The entry 0x2f can't exist anywhere in this entire thing, right?
0x.
Because I can't have something in this that would reference back to L1. So 0x2f
Yeah.
can't exist, right?
Yeah.
Okay.
Yeah, it would be kind of wrong.
That would be terrible because that would allow an application to write to the top level page, its own page table, which means what could happen if that was the case?
It can redirect itself to memory that it's not allowed to have.
Exactly, because if that page table, it was writable by that application, it could essentially map any of its virtual addresses to any of its physical addresses.
And just following up on that, 0x2e can't exist in this cache because you might be able to reference back to L1, but it's not valid because of the e.
Yeah, if it's not valid, you can use the other bits for whatever the hell you want.
Okay.
Yeah.
Yeah. So his comment is like, if this entry was like 2F instead, right? So if this entry was 2F instead, it's like pointing back to itself, which is kind of weird. And if you can access that memory, you can change your own page table.
Especially if the second level page table had an entry which pointed to any page table, any of the physical pages, then you're essentially allowing an application to overwrite the page table. That's what he was asking.
Okay, so yeah, so that was for 1, 2. So we do the same thing, like for any of the ones that begin at 1, we know following this, that this is our L0 page table. So if we had the 122 variant, we would just look up index 3, which is ES. So we keep the offset the same, so our translation would be E2. And then for 113, it would correspond to 90. The 0 means it's not valid, so we would have a page fault at that PTE.
All right. Yes.
I have a question about, from the quiz about simulating bits, the one where it was like simulating a dirty bit in software. So I don't know if you have the question pulled up.
What's your question specifically?
So for the nuances of tracking in software a dirty bit, so the answer was when when a write-only fault occurs in the TLB, then you could then
Mark it dirty.
mark it dirty. So, but the OS implicitly, the OS is also tracking whether the write-only entry in the TLB is actually read-only marker in the TLB is actually read-only, or if it's like a pseudo read-only, in which it's just the transcripts.
Yeah.
Okay.
So I'm not sure I understood the question.
That was that implicit like pseudo.
So think of it this way. Say you have a page table entry which has all these bits, right? Valid, all right? And let's say it has a read-only bit, okay? Read-only. But it doesn't have, let's say, a referenced bit and a dirty bit, and this is the frame number. Okay, so let's say the hardware doesn't support a reference bit and a dirty bit, which is what you need for page replacement algorithms, right? So the idea is, can the software, meaning the OS, simulate these two bits? Now imagine that these bits are currently unused. The hardware doesn't use them. Okay, so these bits are control bits that are used by the hardware. This is unused bits, and then this is the frame number in the page table entry. All right. So the question is, can we simulate this in software? So the idea is, once you have, say, a write fault, so you do a store to a page, and the page is not in memory, in that case, the software, when it gets that fault, the page fault, it can set both of these to 1.
A write fault.
If you have a write fault, all right? So
Ignoring the TLB?
don't worry about the TLB for a second, okay? Imagine the no TLB, because that can be dealt with independently.
Okay.
So imagine that a store is attempted to a page that's not mapped right now, that's not in memory. You get a page fault, and the software, the OS, can set both of these bits, saying this page is referenced and dirty, right? The problem is, what happens if you have a load followed by a store? Okay? The problem is, if you have a load, you map that page, you mark it referenced, you don't mark it dirty, but now when a store happens, you don't get a page fault, right? Because this page is already in memory. It's mapped. So you don't get this. So you are unable to track this in software. So what you want is, in essence, this store should also cause a page fault. The way you do that is you make this temporarily read-only, and perhaps you use another unused bit to say, this is a temporary read-only page.
Okay, that was my question.
Yes, you use a temporary bit here to say this is temporary read-only, not a real read-only page. It's not a text page. It's temporarily marked read-only. Now, because you've got a read-only page, when you get a store, that'll cause a page fault saying you did a protection fault. On a protection fault, you can say, aha, this is a temporary read-only page. I'm going to make it no longer temporary read-only. I will make it read-write, but I am going to set the dirty bit. All right, so this is how you can simulate in software both those bits.
Yep, go ahead.
A load is simply an instruction which reads data from memory, from physical memory, right? The issue is when you do a load, you get a page fault, you mark that page as referenced, right? But now the page table entry says it's a valid page. So next time a store is attempted, there's no page fault. So there's no way for software to simulate that dirty bit unless there's some way to force a page fault. And the software can do that by taking advantage of the fact that paging has these protection bits, like the read-only bit. Right? So we can take advantage of that to simulate the dirty bit. This would not be an issue if the hardware supports referenced and dirty bits. In other words, on a load and a store, if the hardware itself sets these bits, software doesn't have to simulate it.
I want to ask a question on quiz 3. There was a multiple choice asking the number of factors favor larger page sizes, and it says more efficient I/O on a per byte basis to swap is not one of the factors.
For page swapping?
Number of factors favor larger page sizes, and more efficient I/O on a per byte basis to swap is not one of the factors.
What were the other factors?
Other factors.
So I think
Sorry. The correct answer was the working set when measured in bytes is smaller. That was the factor not.
Yeah, the more efficient is a correct answer. Well, it's an incorrect answer in the sense that when you have larger page sizes, the data can be read from disk more efficiently. All right, so it's not, because it said specifically it's not one of them, right? So that's not correct in the sense it actually does help. Having larger pages means you can read them from disk more efficiently.
So large pages you can read from the disk more efficiently.
Mm-hmm.
Isn't that limited to how fast your HAD?
Exactly. So with a larger page, what's going to happen is you will have more sequential accesses. Right? The bigger the page size, you're accessing that entire data from disk for that page sequentially. Right? So there's less seeks happening.
Makes sense.
I made the logs because I talked about SSDs. Yeah.
Well, even in SSDs, sequential accesses are certainly still faster, but yes.
Another factor on what he said, now that we have larger pages, the odds are that we're going to have less page faults because the odds are we requested, like let's say it's a code block, for example, we can get a bigger code block at a point in time and then possibly not have to ask for it again. On a lower page size, we might have to ask for it again more often.
Yeah, also with higher pages, your TLB coverage for the same number of entries, you're going to have larger coverages because your page size is bigger. So with the same number of entries, you cover however many more bytes. So like on your phone and stuff like that, they'll actually drop like a level of page table, so you can have like 2 megabyte page sizes. So, which are called huge pages. That's a fun fact.
What about the working set when measured in bytes is smaller? That was the correct answer.
Yeah.
Yeah, so the working set is just the amount of memory your program uses in a certain amount of time. So no matter what your page size is, it's going to be the same thing.
Correct.
So it will not be smaller.
Okay.
Oh, it's the same, not
Yeah.
bigger?
Not bigger, not smaller, right? Remember, working set is the amount of memory your program needs, the number of unique bytes of data that your program has accessed in the last recent past,
Okay.
right? That doesn't depend on the page size.
I was thinking with fragmentation, larger page sizes could lead to more fragmentation. So
That's true,
more
but
pages would be needed.
no, but that's why it said measured in bytes,
Right.
not measured in pages.
Yeah, because you could have measured in bytes before this course, before you even knew about pages.
And so the page, it's sort of irrelevant, the page size, when you're measuring in bytes, right?
Yep, go ahead.
Could you go over like how the stack grows without getting the invalid memory accesses again?
How the stack grows without invalid memory accesses. So most of the time, most of the time you'll just have like a certain stack size set for you that's going to be all marked as valid.
Okay, so it's just, okay.
Yeah, that's it. There's not really any other tricks with it. For p-threads, you can go ahead. I think in one of my lectures I looked at the stack size. It's 8 megabytes.
Yeah.
So if you go
Well, so here's why it's a little bit tricky. I've done that same experiment on Linux. It's 8 megabytes fixed. On Cygwin, it's 10 pages. It's literally 40 kilobytes, and it grows on demand. As you keep going down, on Cygwin, it's actually different, the emulation. The point is that normally with stacks, they can grow without requiring users to do system calls. That's the difference, the key difference between the heap and the stack. In the case of the heap, to grow it, you have to do the break system call to grow it, right? In the stack, that's not required. The OS will essentially grow the stack or give you a big stack or grow the stack on demand without requiring you to do system calls.
Okay, so with the thing that's like growing the stack on demand, like how does that work? I remember there's a part where you explained it, but.
So in Cygwin, the way it works is as you're increasing the stack, meaning going downwards, as it goes down, the OS seems to just keep increasing a little bit at a time. But if you go, maybe 10 or 15 pages down and try to access data there, it crashes. It'll say segfault.
Yeah, and for some kernels too, they'll just put like the stack pages that should be part of the stack. They'll mark them in the page table as invalid, and then the rest of the bits you can use for whatever you want. So they'll just put a special pattern there that means this is fine, it's going to be used for a stack. So if you get a page fault, the kernel goes like, okay, no, I can handle this. I'll actually back it with a physical page, and then let the program just carry on its merry way after I give it a page.
Okay, thank you.
This is also a question from quiz 3. It says, which is not a factor that favors smaller page size? And the answer is faster TLB handling. So how does TLB handling relate to the page size?
So if you think about what is TLB handling, right? It's just a TLB lookup, and that depends on the number of entries in the lookup. If you think about a TLB, it's essentially a fully associative cache, a hardware cache where that particular virtual address, the page number is looked up in parallel with all the entries. Okay? So the speed of TLB handling is essentially proportional to the number of entries in the TLB. But that's fixed by hardware. So that has nothing to do with the page size.
Okay. So it's because they have no relation.
Exactly.
Following up with the question, like part of it is because the offset is the only thing that's going to change. The TLB actual entry just points to a page. That doesn't change. The offset is what changes, in a sense. If the page size is smaller or larger, then the offset changes.
Makes no difference because the speed at which the TLB can look that up entirely depends on the number of entries there are. The more the entries, the slower it'll be to look up those entries in parallel also, just the way hardware works. That's why the TLBs tend to have very small numbers, 64 to 256 entries, because they really want to do that fast sub-cycle, parallel lookup. Can you speak a little louder?
Reduce internal fragmentation, the first option.
Yes, it does help. Smaller page size will reduce internal fragmentation.
Yeah, everyone figures that word. Not.
We're just confusing you.
The quizzes had a lot of questions that say like this knot, for example, like you want to read it very closely. Would you say the exam is more like that, or the exam is more straightforward?
We're still working on it.
Oh,
As of right now, the exam's much more straightforward. Okay.
Because we're switching from the online to the hard copy, we're still working on it. So I think it'll be closer to some of our older hard copy exams than these kind of papers. So we're not going to have as many of these multiple choice and true false kinds of questions.
depends what we set the exam as. Right now, it might be.
It's really in
slightly-
flux. Honestly, I haven't looked at the questions yet. How about that?
Yeah.
So-
As it stands right now, it's probably slightly easier, but not too bad.
we're trying to have something where, you know, we try to keep this exam similar to these, but not completely, just because of the nature of the exam. Okay, but it won't be. We'll try to be nice to you guys. How about that?
Yeah, try to be nice. The exam covers the whole course, so
Yeah.
hopefully equally weighted towards everything.
Is there less weights on topics that's been on quizzes?
No.
Same weights?
Same weight for the entire course.
So no file system bias or extra question.
That's right.
So on the topic of niceness, so let's talk about part marks. So there was a quiz question that was talked about using exec VE and what the printout of a program would be, which is similar to a past either final or midterm that had a question that talked about forks and what would be printed out. If you explain your thought process for how the trace works and what gets printed out, how do part marks work in all of this?
Sorry.
How do part marks work in all of this? Like, let's say my answer is like dead wrong because I messed up my first fork, and then everything's wrong because of that. How does that get marked? Would you say?
We don't have a marking scheme until we have a question.
Yeah, and it depends what you write. If you
Yeah.
just write an answer, it's like, I don't know.
Yeah, if you write a total wrong answer, exactly
If you
right.
start writing out like, you know, parent-child relationships and stuff like that, and then I can follow your answer, I'd be like, okay, they knew what was going on. Like, a lot of it's just like marking, it's like a judgment call. Some stuff you can't even make a rubric for because you get some interesting answers. And by reading them, you can kind of tell, hey, is this person just making something up or did they make a mistake?
Sometimes during the marking, we make up a rubric based on the fact that we see the same error again and again, and then we are like reverse engineering the thought process because you haven't said that, right? We're like, oh, everybody, the answer should have been 0, 1, 2, 3, 4, but a lot of people have had like 1, 2, 3, 4, not 0, or something like that, right? So then we kind of say, okay, maybe in that case, since many people are sort of misunderstanding, we'll give some part marks for that case.
So always with writing down your thought process.
I think it does help that at least you explain your thought process if you have time. Yeah.
So are we expected to write on any code in the exam?
Sorry?
Are we expected to write any code in the exam?
No. So, fair things. Writing code just from scratch, probably not. Reading code, adding probably locks and other synchronization stuff.
Or looking for bugs. So the idea is we try not to have you write code because it's virtually impossible to debug your code. Our TAs go crazy because even if we ask you to write 5 lines of code, remember 5 lines of concurrent code can have, you know, literally infinite interleavings, and now we're trying to figure out what you were thinking. So we try not to do that because invariably code is buggy. So what we do is we give you the buggy code you've shown us in the past and tell you to fix it.
Yeah.
Could you go over what the reference bit is for? And briefly, the general idea.
Once again,
Could you go over what the reference bit is for? Maybe
the reference bit.
general idea.
Yes, so if you remember all our page replacement algorithms, the ones that took locality into account. The simplest was FIFO, which didn't take locality into account. It just said whichever page was brought into memory first is the one, or the earliest, we're gonna kick it out. But that doesn't work so well because it doesn't take locality into account, right? Now, if you want to take locality into account, you need to know what pages have been accessed. And that's the point of that reference bit. It's saying this page has been accessed recently. And because it's been accessed recently, the page replacement algorithms that take locality into account will try to not evict that page. And as part of not evicting that page, what they do is when they look at that page and find that it's referenced, they unset that bit. So often hardware will set the reference bit and the software will unset that bit saying, okay, I looked at it, I have given you an extra chance, I've not evicted you, but the next time I look at it, if I still see it's not referenced, then you're eligible for eviction, for instance, with the clock. On the other hand, if in between the last time I saw you and now I'm seeing you again, If you've been accessed, the reference bit will be set and you'll get another chance.
Yes, and the idea behind like anything that uses a reference bit is to make the actual implementation fast. Because if you try and implement LRU just straight up like using timestamps or something like that, or you have to scan every single page every time you have to make a decision, it's going to be really slow. So a clock is kind of like an approximation of LRU that you can implement way faster. As some of you probably noticed from your like lab 5, if you implemented LRU, it was probably slower.
Although in the case of file caching, LRU is not as slow, but with page replacement, LRU is just simply infeasible. Because in principle with LRU, every load and store access changes the LRU order, right? Whereas in the case of our lab 5, it's every file access, and file access means accessing a lot of data from disk. So manipulating a LRU list in memory is pretty fast compared to accessing data from disk. But in the case of page replacement, LRU is just not feasible because every memory access potentially changes the LRU order.
It seems the questions hardly ask those bits. Usually they're just some bits occupying the space in the virtual address.
I'm not sure I understand your question.
How could a question like ask how the bit works, how reference bit works?
We'll just give you a page replacement algorithm to simulate, and then we get to know whether you understand how the page these bits work, right? Yeah.
Having taught this course for some time and seeing a lot of exams over the years, what would you say is usually the topic that students don't understand or mess up on very often on exams?
Page tables.
Page tables, if we give them those dumps. That's called the page table memory dump. And it invariably leads to problems because of two reasons. One, people don't understand where the page is in the page table dump. And the second is they often do the wrong indexing. Often if you start indexing from 1 instead of 0, that becomes an off by 1 error.
For this question is specifically for multi-level page table. So I want to know more about like number of bits for the page table entry. So just for example, you have a physical frame number of 12 bits, right? And you're trying to reference it. So in a single level page table, you will have the physical page number and maybe some other some bits. But that's only for a single level. So for multi-level, say 3 level, let's split this up into 4, 4, 4. So every page for every one of these like smaller sub-page tables is going to be indexing 2 to the power 4, and that's not 12 bits, that's 4 bits. So when you be taking the lowest 4 bits in that case, the page table entry remains the same size.
So given that page table, the virtual address, the lowest bits are the offset, right? The page offset. The rest are the page number. The rest of the bits are the page number, and you take pieces of that. The highest bits are for the top level page table. The next set of bits are for the second level page table. The last set of bits in a 3-level page table scheme. The last set of bits would be for the 3rd level page table.
So in this scheme, how large would the page table entry be?
So it depends.
Okay, yeah.
Okay, here, make up a bunch of numbers. We'll just make up a question. So you want 12-bit physical page number?
Yeah, sure.
Okay, what else do you want?
How many bits for the virtual page number?
Virtual address or virtual page number? How big do you want it?
Let's do 9.
9-bit?
Yeah.
Okay, this will be a weird machine. Page size.
Page size. Let's.
That has to be a power of 2.
Yeah, yeah.
Wait, can we do 8 bits and let's do page size will be 2 to the power 2. 2 to the power 2.
Okay, 4 bytes.
4 bytes.
And then the physical page number is 12, you said?
Yeah.
Okay, so first do you want to tell me your page table size or page table entry size, or should we come up with something reasonable?
Oh, that was actually my question.
Oh.
determine the page table
So-
size from this?
Yes.
Yes.
See, the page table entry size is entirely dependent on the amount of physical memory you want to support. It has nothing to do with the virtual address, the size.
Okay, that's based on the
That's based on those first 12 bits,
Okay.
right? So your page table entry must be 12 bits to be able to support physical pages or 12 bits of physical pages.
Okay, so,
Oh, and then also at least one
Bit for the valid,
bit.
right?
right.
That's like minimum you have to have. So it has to be at least 13 bits in this case. So you probably just round up to the next powers of 2. I'd call it 2 bytes.
So that's the question, the next level question would be, so you have 12 bits for the 13 or 12 bits for the address of the page table entry. Say now you have
No. You used the wrong terminology, so I want to clear. We have 12 bits for the data of the page table entry, not the address.
frame number,
Sorry?
the page frame number.
Yes, the page frame number is those 12 bits at the top, plus at least a valid bit, and let's say round up those 13 bits to 16 bits, right? So we have 3 unused bits, 3 unused control bits, 1 valid bit are the 4 control bits, plus 12 bits for the page, the frame number.
So say now you have a multi-level page table. The first level of the page table, you don't need 12 bits, you need 4 bits.
So in this,
That's an independent thing.
yeah, so for multi-level page table, the design is always on a single page. I want to fit a bunch of page table entries, and I want to know how many I can fit. So here, our page size is 4 bytes, weird thing, and our page table entry is 2 bytes. So how many could we fit? 2. So this would be a very long table. So we can fit 2. So we have 2 page table entries. How many bits do we need to distinguish between 2 things? 1. So for every level, I have 1 index bit. Oops. So if I have a 8-bit virtual address, what that's going to look like is how many, so I have 2 bits for my offset, and then to fill up the rest of those 8 bits,
Let's ask that question. How many level page table? We have 2 bits for the offset. How many bits are there for the page number? If you go up a bit, the virtual address is 8-bit, right? So how many bits do we have for the page number at the bottom? 6. All right. So how many level page table do we need in this example? 6. Each
So-
bit
so
will take you to 1 level page table. That's a great example that should clarify. The important thing to realize is the size of the page table entry is determined by the amount of physical memory. The number of levels of the page table is determined by the virtual address. And those two are orthogonal. And that's why I think maybe there's some confusion about, you link up the size of the page table entry with the virtual address. No, there's no correlation there, more or less, right? Because it entirely depends on how many bits you need for the frame number.
In solving this question, we assumed that a page table fits in a frame, right? We had to assume that.
Yeah.
Yeah, that's usually the design because then everything's aligned to a page. And if you need another page table, you just grab another page. And it's
It makes the kernel allocator easier. All you have to do is allocate 1 page at a time.
Yeah, and there's no special handling, no thing like weird.
Sometimes on past exams, they don't allow it to be fit into the timeline.
Yeah, we just wanted to mess you up even more.
Should virtual address be longer than PPN?
Yes. In fact, on modern 64-bit machines, you have 64-bit virtual addresses. The physical addresses that are supported on Intel can be far less. Often they're,
No, generally on machines we want lower virtual because like ARM, they will use a 39-bit virtual address, because every time you have a larger virtual address, you're going to add another level of page table probably, which is going to make everything slower when you have to actually have like a TLB miss or anything. So like ARM will do a 39-bit virtual address, and if you want more, you can step up to like a 48-bit virtual address, but it's going to be slower. But the hardware can support address 64-bit things if you want. But even on like ARM, they support 54 bits of physical address. Yeah.
The linkage between the two is not there for exactly the reason that with virtual memory you get this nice property that you write to the architecture, not to the amount of physical memory that you have.
Yeah.
That's a wrong point. What do you do if it doesn't fit?
What do you do if which doesn't fit?
Like if the page table doesn't fit in the page doesn't fit in the page frame.
Like the page table entry can't fit the page frame?
Like what Rohan was saying.
But the page table is larger than the actual frame.
Yeah.
Yeah, that's just weird.
It's possible most kernels won't do that just because it complicates memory management.
Can we always assume that they won't?
Yeah.
Yeah, unless the question's trying to be like really tricky and be like one of them was like, yeah, I use a page but I divide into 4, so it's actually 4 page tables. Or
There have been hardware that do that. It improves internal fragmentation. All right. So there have been some X hardware, older hardware that does things like improving. When memory is expensive, you want to think about these things, right? Today, DRAM is still expensive, but maybe not as expensive. You want to simplify all of this as much as possible. So it's not used.
yeah.
Sorry, where does the 2 bytes come from for the difference in percent?
So it has to be at least 2 bytes because our physical frame number or physical page number is 12 bits. So that we always store that in our page table entry. And we'll always have to store at least 1 bit to say whether that entry is valid or not. So it needs to be at least 13 bits. So typically you just round up to the power of 2. So I can use 4 control bits, fit it in 2 bytes, no problem. Yeah, I couldn't do 1 byte smaller, otherwise I'd run out of bits, but it could be 4 bytes if you want, and you just don't use a bunch, but you're going to fit less page table entries on a page, so you probably don't want to do that.
Right. And aside the number of page table entries is dependent on the virtual assets. And
That's right.
yeah,
One way to think about it is the number of page table entries is dependent on the virtual address. The size of the page table entry is dependent on the amount of physical memory. So the other type of question that people tend to have problems is with synchronization and locking, right? Because that involves often thinking of interleavings. And as you've seen, we've asked you questions like that, like for instead that printer problem, right? With that if and while example where if that happens, what kind of problems will happen? And you have to sort of really think through potential interleavings where, you know, what's happening when somebody is going to sleep, when somebody is sleeping, what happens if somebody's arriving, somebody's leaving. So that takes a little bit of time, but you know, just be systematic, think of the key sort of events that are happening, and that will help you see, you know, potential interleaving issues. Where are we time-wise?
104, so I think
Okay,
we're
we are maybe the last question.
Yeah.
Yeah, and so the reference bit is just when you have referenced it, you set it to 1. But you mentioned locality. If I reference 1 page, do I set neighbor pages also?
No. Locality has to do with what the program is doing, right? So if the program accesses the next page, it'll get set. We'll say that that program has spatial locality. On the other hand, if the program accesses random pages, then the reference bit of random pages will get set, in which case we'll say that that program doesn't have very good page locality.
Locality is referring to the program.
Behavior, exactly. Whether that program is accessing data that's spatially close, which is spatial locality, or temporally close, meaning the same data it keeps accessing in short periods of time.
And how does setting one reference bit help?
Because for that corresponding page, when the page eviction or the page replacement algorithm runs, it says, I won't evict this page because since you've accessed it recently, I will not evict it.
Like quickly with respect to exam coverage, so you posted what won't be covered.
Yeah.
Is this like, because in previous exams, you've asked questions where you want the students to extend, you give them something that they haven't seen before, but apply what you taught. Are those fair game?
Of course they are fair game. Of course.
But they're not, so like, we won't get a question on SSDs asking us to apply our INO knowledge.
No.
A completely new file system you could ask?
Of course, we tell you here's the basic file system we've talked about, and here's the new design you're coming up with, and think about it.
But it just won't be SSDs.
Yes, it will not be SSD.
Yeah, no, SSDs are a real, it needs another 1 or 2 weeks to really describe what happens in an SSD.
So is it worth it or not to take like a cursory glance at all that material that's not being covered? Because of that extension question.
No, the extension won't be on things we haven't covered together. The extension would be on whatever we have covered, possibly something extended. Yeah.
Yeah, the list I posted is not going to be on the exam in any flavor whatsoever. Okay, cool.